Hi students, in this lecture we are going to compare kinematics 1D with rotation about a fixed axis. Let us see. In kinematics 1D we have taken x as a position coordinate. In this theta, this is angular position, velocity, omega, acceleration, this is alpha, force. We are comparing this with a torque. According to Newton's second law, net force F net equal to ma bar, or you can say ma. It is now tau net equal to, it is I alpha. So comparing A with alpha, comparing torque with the force, net force equal to mass into acceleration, net torque equal to I into alpha. Or we can take net force F bar net. This is equal to rate of change of linear momentum with respect to time. Now same thing here, same thing. Net torque equal to, wait, I have taken down here. It is rate of change of momentum. Rate of change of momentum. This is dp bar. Okay. So net torque equal to rate of change of angular momentum dl bar by dt. Next, kinetic energy is half mv square, and this is a half I omega square, right? Or same thing in terms of momentum, p square by 2m. This is L square by 2y. Let's see kinetic energy. After that, we can take work energy theorem. W net, that is equal to delta K. Now here also same thing. W net equal to delta K. So here delta K means a half m v2 square minus v1 square. This is a half I omega 2 square minus omega 1 square. Okay. And if you see definition of work done, integral f bar dot ds bar, right? So coming to here, same thing, integral tau bar dot d theta bar. Okay, right. So we have taken work done, net work done, kinetic energy, force. Next we can take momentum impulse theorem. So we have learned net impulse. Net impulse is equal to change in momentum of the particle, right? So here net impulse, or we can say net angular impulse, okay, that is equal to change in angular momentum. Okay, and next see what else left here. Next we can focus on dp bar equal to f bar net into dt, right? dl bar equal to tau net into dt. Next see what else we have take here. Yes, we have to take power here. Power equal to, so power f bar dot v bar. Now here also power equal to tau bar dot omega bar. Okay. So like this we can compare kinematics 1D. or I can say linear quantities with angular quantities. Okay, so power, impulse, work done, net work done means work energy theorem, kinetic energy, net force, torque, acceleration, alpha, velocity, omega, x, and theta. Okay, so now by using this comparison, we can solve problems. Let us see now problems. Right, so the first problem, a particle of mass m is whirled in a circle of radius r with a constant angular velocity. Its angular momentum is L if the length of the string is now becoming half, keeping angular velocity the same. The condition is omega not change. Okay, by keeping omega same, new angular momentum is right. So first we have to focus. It is circular path, omega constant. Now what we are doing is length is becoming half. Length becomes a half without changing omega. What happens to angular momentum? Now see how to get it. So it is given that omega constant. Omega constant. We are calculating angular momentum. So we can take it as I omega. It is now following circular path. Circular path. I value mr square. Right? I value mr square. Omega only. Now condition is length is becoming half. That means r becomes a half. Mass constant, omega constant. If r becomes a half, L becomes L by 4. It becomes L by 4, right? So very simple and direct. See next one. See the question given. Two bodies with moment of inertia I1 and I2. Condition is I1 greater than I2 are rotating with the same angular momentum. If K1 and K2 are their kinetic energies, then so given moment of inertia, kinetic energies with the same angular momentum, L value same. Okay. Then see how to decide this. So we have seen just now kinetic energy equal to half I omega square, or writing this same as L square by 2y. Now in this case, L value same for both, right? Since L same, K into Y is a constant. K into Y is a constant, right? Then see what's the option given here. K into I constant. I1 is more. I1 is more means K1 is less. So K1 less than K2, right? So very simple one. See next one. The moment of inertia of a body is 1.2 kg meter square. Initially, the body is at rest. In order to produce a rotational kinetic energy of 1500 joule and angular acceleration of 25 radian per second square must be applied about the axis for a duration of. So see the condition given here. Moment of inertia given 1.2. Body at rest initially. We have to produce 1500 joule kinetic energy, alpha 25. So how much time we have to apply this one? Okay, let us see. First write down the given data, given I value 1.2 kg meter square, and we have to produce a kinetic energy of 1500 joule and alpha given 25 radian per second square. So how long we have to provide this acceleration, right? Right. Initially it was at rest. That means this is a final kinetic energy. Initial kinetic energy is 0. Then see how to start the problem. See, coming to here, alpha 25. So kinetic energy means what we can write. Since alpha constant, omega value, sorry, we have to find out time. Okay. So we have to find time. Then see where to start the problem. Let us do one thing. Take work energy theorem. W net is equal to delta K. Okay. Because initial K value 0, finally K value is known. Means delta K is known. Alpha is given and I is given. I into alpha gives net torque, right? I into alpha gives net torque. See how much? 1.2 into 25. It is equal to 30, right? 30 Newton meter. So net torque is known. So net work done is equal to delta K. Therefore, net torque, that is 30, into displacement, right? Net torque into displacement. Displacement how much? Displacement equal to half alpha t square, right? Because initially it was at rest. So displacement equal to, because alpha is a constant. So net torque into displacement is half alpha t square. This is equal to delta K, right? Let us now simplify this. 0, 0. Next, I can take 2 here, 300. This is now 3. So remaining 100 by 25, 4. That means t value 2 seconds, right? Now do one thing. Let us solve same thing in a different way. So here we have taken using work energy theorem, right? So here, since the kinetic energy is known, this we can take it as method 1. We have taken work energy theorem. Let us do one thing. Kinetic energy half I omega square equal to half I omega square equal to 1500, right? That means if from this what we get omega value. This is now 0.6 times and 0.6 here. See how many times? So omega square. That means omega comes out to be 50 radian per second, right? Since alpha constant, omega equal to alpha. Alpha is 25 into t. That implies t equal to 2 seconds, right? Is a point clear? Or do one thing, solve the same thing. So take it as method 2. Let us solve the same thing in a different way. We want to find out time, right? And we are knowing what is net torque. So into net torque into time taken, that is t. This is giving us net impulse. I am writing here. Net impulse is equal to change in angular momentum, right? Net impulse equal to change in angular momentum. So this is now net torque 30, which is a constant. Okay. Because we are calculating torque as, sorry, impulse. Net angular impulse is defined as integral tau net into dt, right? It is just like f bar into dt. This is now angular impulse, which is equal to change in angular momentum. Now writing same thing here. Since net torque is a constant, we can take this out of integration. So remaining is only integration of dt, right? That becomes t. So 30 into t. This is equal to change in angular momentum. And we have learned that kinetic energy equal to L square by 2y. Okay. This is actually delta L. Delta L. That is equal to final value minus initial value. So final value how much? Root of 2 I k, right? Substitute that here. See what we get. 30 into t is equal to root of 2. I value 1.2. K value 1500. This is equal to how much? It is equal to 60, right? This value 60. So this is now here cancelled 2 times. So t equal to 2 seconds. So like this, we can use Verkanaichi theorem or net angular impulse equal to change in angular momentum, right? Otherwise, simply taking kinematics, first finding omega value, then omega equal to alpha t, then we get the value of t, right? Let us see next one. So answer is 2 seconds. Right, see the question. A solid sphere and a hollow sphere of the same mass and radius rotate about their diameter with the same kinetic energy. So given same mass, same radius, about diameter, same kinetic energy. If torques of equal magnitude are applied on them, the ratio of their angular displacement before they are brought to rest. Okay, ratio of angular displacement before they are brought to rest. Let us see. Given equal torques, same kinetic energy. Right. Given solid sphere, hollow sphere, both have same mass, same radius, same kinetic energy, applying same torque. We have to get ratio of their angular displacements. Take it as theta1 and this is theta2. That ratio we have to calculate. So before they are brought to rest, then see, initially both have same kinetic energy. Finally also both having same kinetic energy because both are coming to rest. Okay. That means delta K is known. So we can use work energy theorem. Net work is equal to delta K. Delta K is same for both. So this is now net force. So here we have take torque, right? So tau into d theta. This is angular displacement, right? Just like F into displacement. This is now torque into angular displacement. And condition given that same torque is applied. Same torque. Delta K is same for both. When these two are same, delta theta must be same. That means the ratio will be 1. Okay. Right. Let us see the next one. So answer is 1:1. That's the next what is given. Two rigid bodies have the same angular momentum about their axis of symmetry. If the same torque is applied about their axis, the ratio of times after which they will be stopped is almost same as the previous one. So what is saying here? Two rigid bodies have same angular momentum about their axis of symmetry. Same torque is applied. Ratio of times after which they will be stopped. Ratio of times we have to calculate. Let us see. Given same angular momentum, same torque is applied, we have to find ratio of times when they come to rest. L value is same for both. When they come to rest, again same L value. So initial value is L, initial value. Final value 0. They come to rest. That means we are knowing delta L and we are interested in finding T value. Since delta L is known, the best one is using net angular impulse equal to change in angular momentum. So writing here, net angular impulse is equal to change in angular momentum. Now this is same for both. Initial value same, final value 0 for both. Delta L same. This is now net torque into time taken to come to rest. And given same torque is applied, same torque is applied, same change. That means T must be same. That means answer is 1. Okay. So it is option C, right?